Welcome back. Well, now we are going to look at the sampling distribution, not for the sample percentages this time, but for the sample means. And so what you can go ahead and do, if you haven't already, is download that data file called ticket sales and go ahead and import that into StatCrunch now. So I want to kind of motivate what we're doing with a problem from business. And so let's suppose, for example, you are, say, the manager of a regional airline, and you're looking at airline ticket sales to Orlando. And that's what is in that data set, by the way. And, evidence seems to suggest that the ticket volume stayed the same, but the overall revenue has decreased. And the question is, how do we distinguish signal from noise? How do we know what is an actual trend versus just a variation? And so let's just suppose this was the graph of the ticket sales. And the recent data that we have, called past ticket sales, shows us that the average ticket price was roughly $350.96. So that's the past average of the data that we have recently. And now we see this little blip. And what we want to figure out is, are prices actually decreasing? Or is the cost of the ticket that people are buying actually decreasing? Or is this just part of the random noise in this trend? And this is a problem that is becoming increasingly important to business. So really, to have a competitive edge, businesses really work very hard to analyze this sort of data well. So notice that, for example, if people really are buying lower tickets, okay, you might want to lower ticket costs to try to offset that. But if you lower the ticket costs and it really isn't the case that people are buying lower tickets, it's just a momentary dip, you're going to lose money. And you might imagine whenever we're dealing with time series, these sorts of problems occur a great deal in stock markets or any sort of financial instruments that we're looking at. This is a really important problem. How do companies make decisions quickly? Because in order to make it quickly, they can't use a lot of data. And if they don't do it quickly and their competitors do, they lose their edge. Now, here's an interesting question that is related, although it won't seem that way initially, which is, why do we use the average? Why do we use the mean? And when you were working through Module 3 on exploratory data analysis, it might have occurred to you that the median was always the safe choice when we wanted to describe the center of the data set. When we had skewed data, the median was the correct choice. When we had outliers, the median was the correct choice. And when we had a symmetric data set, the mean was about equal to the median. So the question is, why do we care about the mean at all? Now, those things that made the mean actually really not good for describing the center make it good for inference. Because notice, the thing that made the mean bad in these cases was the fact that it was sensitive to changes in the values of the distribution. So when we had outliers, like in the Mr. Burns case, that one value, the mean was very sensitive to it. And of course, with skew, we saw the mean gets pulled out towards the tail. And this is actually true in general. Whenever we have a distribution and the shape of those values change, the mean changes too. And so it's that sensitivity of the mean that actually is really important. While it makes it not always good to use as the center of the distribution, what it really is good for is detecting if a change occurred. Just like that change we showed in the previous slide with the average of the ticket prices. So this is how we're going to leverage the mean. And so just to kind of flush this out a little bit more, the idea is, this is the logic behind what we're doing, as the population changes, the distribution of the values changes, the mean's going to change. So for example, if the past sales looked like this, and we had an overall price increase, notice that the distribution shifts to the right. Well, again, the mean's going to change. If we have some distribution, but now let's say maybe high-end items begin to sell more, the distribution is going to become skewed. And we know what happens with skewed distributions. The mean gets pulled out towards the tail. So again, the mean's going to change. So let's think about this in the context of our problem. We want to ask the question, how does the sample mean tell us if the population's changed? And so we have this logic. Change occurs, the distribution of the values in the population changes, and that should change the population mean. So if we think about our problem, we have the past sales in the first column, and the second column are recent sales. So these are the most recent sales. We have 300 tickets, and their average is $347.84. And there's two possibilities for what's going on. The first is that they're just a sample of the old population, our past sales. And the other hypothesis is that a change has occurred, and now they're a sample from a new population. So the first possibility, no change occurred, the sample comes from this population, so that average is just a momentary blip, okay? It's just a variation that we get naturally when we sample from this distribution. The other possibility, though, is that something actually happened, and there's a new population, and this is a sample from the new population where the mean's not going to be $350.96 because since the change occurred, the population changed, and the population mean is going to change also. So how do we think about this? Well, we have a problem in that if a change actually occurred, we're not going to be able to tell if the population mean changed. Okay, we don't have the whole population. We just have a little snippet in time, a little sample. So this really presents problems. You know, we have our past population, maybe a new population, we don't know. Okay. So our recent sales could be a sample from this new population. But the problem is that this number here, mu from our past population, is a fixed value. And we know that the sample mean is going to change from sample to sample. So we can't say anything about the population mean based on a single sample mean because the sample average is going to vary. So what is the solution? So we can't say anything about the population based on a single sample mean, but here's what we can say. What we can do is we can compare our one observed sample mean to sample means that are taken from the past population. And so this is the idea of what we're going to do. We're going to take samples from that past population that are random and of the same size. And for each of those many samples, we're going to compute the sample mean. And then we're going to plot all of these sample means. We're going to get a distribution, okay? And now we can ask the key question, which is, if we look at this distribution of sample means from our past population, does our observed sample mean look like it comes from sample means from the past population? So this is a really kind of involved train of thought here. So let me kind of show you the pictorial notion of what's going on here. So I have some population that I know, my past population. I'm going to draw random samples and compute the sample mean from each of these. Okay? And so here you can see this is the population mean, and these are the sample means. Notice each of these is not a data value. This is a sample mean. And then what I'm going to do, and I could compute the z-score if I wanted to, right, from each of these, okay? What I'm going to do now is I'm going to look at my observed sample mean, right? And what I want to know is how likely is it that this observed sample mean could come from the sample means I get from this population. And that's the game I want to play. That's what I want to look at here. Notice that if I get a value way out here, it has like a z-score positive 3, it's very unlikely to come from that population because I know that really high z-scores, it's unlikely. So this would be evidence that there was actually a change, right? This would be evidence that my sample mean didn't come from the old population and that it came from the new population. On the other hand, if I got a z-score maybe around 1 or 2, right? Well, that's not that unlikely. That could happen by random chance. So this would not be strong evidence that an actual change occurred, right? And so this is how we're going to look at this problem. This is what we're going to do. So what we're going to do first is we're going to go ahead, we're going to download that data set if you haven't already, and we're going to take a whole bunch of samples. We're going to be on the calculator, right? So the calculator can just take a gazillion of these. We're going to take 1,000 samples of the same size that we're working with. We're going to compute the means, and then we're going to go ahead and plot them. And the question is, how do we do this in StatCrunch? Okay, we're going to do all of this in StatCrunch. Okay, so again, this is kind of the idea, right? Here's my population. The computer is going to keep on taking, samples of 300 tickets 1,000 times. We're going to compute the sample mean for each of those samples, and this is going to be the data that we work with. And what I want to impress upon you is how different this is than what we're used to. Up to this point, probably nobody in this class has worked with samples of samples. Statisticians work with them, but up to this point in your career, you won't have seen this. Because if we had a bunch of samples, what would we do? We would just glom them all together. We would just combine them to get one big sample. So this idea of having a sample of sample means is really a new concept for us. It takes us a while to kind of wrap our mind around this. So let's see how this is going to work. So here's how we're going to do this in StatCrunch. We're going to go into StatCrunch after we've imported the data set and click on Data and Sample because I want to take samples. And so let's go ahead and do that. I'm going to work alongside you guys. So I'm going to go Data, Sample, and a new window will pop up. And so I'm going to have to tell StatCrunch how to do the sampling now, okay? So here's what we're going to do. We're going to specify a couple of things. First, we're going to tell it what variable I want to take the sample from, the sample size, okay, which is going to be 300, the number of samples of size 300 I want to take, which is 1,000, and finally, I want to click Sampling with Replacement. And what that means is that every time StatCrunch takes a sample of size 300 and then computes the sample mean, it puts that sample back in. So the next time I choose a sample, I'm again sampling from the entire population. So let's do those 4 things first, and we'll come back to the 5th one, because that's a little complicated. So here I'm going to sample this, my population of past ticket sales. And my sample size is 300. I want to take 1,000 samples, and I'm going to sample with replacement. Now, what I want to do, if I just click this button, this whole screen is going to fill up. Okay, it's literally going to show me the data for 1,000 samples of size 300, which I don't want. All I want are the sample means. Remember, again, the sample is just a means to an end. All I want is the means. So I'm going to tell StatCrunch here to compute the mean for each of the samples. And this is where we really have to be careful. The syntax matters. So first I'm going to type means with an open parentheses. So I'm going to type mean, and I'm going to type open parentheses. And then I'm going to type in quotation marks sample with open parentheses. Okay? And again, yours is going to vary a little bit because this is not actually this is I changed the variable name a little bit, so it's actually going to be this. Okay. And if I wanted to, I could just copy and paste this. On yours, it'll say this. Okay. But I want you to enter it because I want you to get used to doing this command. Okay. So again, double quotes, sample, open parentheses. So let's try that. So inside of this, I'm going to put double quotes twice, and then sample, lowercase, open parenthesis. And now I'm going to type the name of the variable, and you have to type it exactly as it is with spaces and everything, okay? So inside of these open parentheses, we're going to type past, space, ticket prices, space, USD in parentheses. And that will give us our sample means. Oops. Let's see, what did I screw up here? Oh, sample has to be capital S. There we are. Okay, there we are. Yeah, so the syntax matters. Notice I didn't put a cap. Notice that mean is small m, but I didn't put a capital S and it screwed me up. So it has to be like that way, literally verbatim. And so these are my 1,000 sample means. If you scroll down, you'll see there's 1,000 sample means. Okay. And these values on these rows have nothing in common. Okay, this is my past population. These are recent ticket sales. And these are the 1,000 sample means that I drew from this past population. All right, good. And you might have to pause it and kind of play around with it. And again, be really careful with syntax. Okay, so let's go ahead and do some exploratory data analysis. Okay, I'm going to go ahead. I'm going to plot these. Okay, I'm going to take this off. By the way, this is from a previous class. Here we go. And so I'm going to do exploratory data analysis. I'm not going to bother looking at the data. I'm just going to go ahead. I'm going to get the mean and the standard deviation anyhow. I'm going to go ahead and just compute the max and the min, okay? So let's first go ahead and plot the data. Histogram. I'm taking the means of my samples. I'm going to do relative frequency. And I'm going to do something we haven't done so far. What I'm going to do is I'm going to overlay on top of the histogram a nice smooth curve that corresponds to the best fit normal distribution. You don't have to do this, but it's actually kind of nice. Okay. I'll put the mean and the median in like I normally do. And I need to put a title and a label. And this part's important, okay? So my X label is going to be averaged ticket price. And this is going to be relative frequency. And finally, my title. Okay. So I'm going to put distribution of 1,000 sample means of size 300 randomly drawn from population with mu equal to, and the mean for the population before was what, 350.97, I want to say. Let me just check. .96. Okay. So this is that past population that I'm drawing from. Come back here. $350.96. And we're ready to go. And if we had to describe that, okay, it's clearly symmetric unimodal, right? No apparent outliers. The center is going to be described by the mean, since it's symmetric, and the width by the standard deviation. And so I'm going to copy and paste this first. And I'm going to compute the summary statistics. You guys know how to describe data sets, so I don't have to do that for you anymore. Whoops. And if I compute the mean of these sample means, okay, I have a sample of sample means, I'm going to compute the mean and the standard deviation for them, okay? So here we're going to go back up to summary stats. And I'm going to look at my sample means. And I'm interested in the mean and the standard deviation. And I see what that is. That's $350.81 for the mean and $5.99 for the standard deviation. And I'm going to copy and paste that because we're going to use it a little later on. Okay, and there we are. Just reformat our table here so it doesn't take up quite so much room. Okay. And there we are. Whoops. Sometimes the key that the resizing and the moving it's big. There we go. That looks good. Okay, good deal. Probably as good as it's going to get. Okay. All right. So what can we say with this? Okay, what can we actually do with this, right? So let's see how we're going to use this now. Oops. So notice that, and by the way, my observed sample mean changed. I did this a second time, okay? So if I look at my observed sample mean, it's 350.8. I'm sorry. This is the observed sample mean from the recent data, okay? I want to know if it looks like it comes from the past sales data. And if you look at this, let's go back to the histogram here, okay? I'm going to blow this up a little bit. So this is what sample means look like from the old population. And here's our data value, right? About 347. It looks like it's pretty likely to come from the old population, right? It's not out in the tails. It's not a value that's unlikely to occur. So we know already that we're probably going to find that this is evidence that the population did not change and it's just a blip. So we're not going to do anything. We're not going to adjust our prices or anything like that. So we can kind of see this from the plot. But what if we wanted to do a little better? I mean, what if we wanted to, say, for example, to actually compute the value without having to do simulations? Because it's going to change from simulation to simulation, right? How would we actually do that? So here's the key. We noticed that those sample means looked like they formed a normal distribution, and they do. Okay. And so it turns out that just like the sample percentages had a normal distribution, so do the sample means. And so it's super important, and I can't emphasize this enough. And this is the one thing that I think if this is not really emphasized, no student in the class would get this. It's that the sample mean has its own distribution. So here's what I want to show you. Notice that here, right, this is the distribution for the sample means. What does the distribution for the population look like? Well, let's check it out. I'm going to do a histogram of the values in the past population. Notice they don't look anywhere near the same. Okay? These are the values of my variables. These are individual ticket sales. These are sample averages. Okay? Sample means. The variable and the estimator do not have the same distribution ever. They have different distributions. The sample mean lives in a different distribution than the variable value does. And one of the ways that we try to emphasize this is through the use of our notation. So pictorially, here's what we're trying to say. We have the variable, which is x, and our estimator, the sample mean, which is x bar. So the ticket sales have a mean and a standard deviation in the population. When I start to draw samples, though, and I look at their distribution, they're also going to have a mean. But instead of using mu, which is the notation for the population mean of my variable, I'm going to use mu sub x bar to indicate that it's the mean of a different variable. Notice the sample means a variable also. It's not a variable in the sample, but it varies from sample to sample. Same with the standard deviation. If I take all the values in the population, they have some population standard deviation, and we said that was sigma. But if I could hypothetically imagine choosing the samples over and over and over again and computing the means, the sample means would also have a standard deviation, sigma sub x bar. Okay. And so we can see we're talking about this nice blue curve. This is the population of sample means. And again, this is a really difficult concept to wrap your mind around. It's easy for us to be able to envision a population of variable values. You guys can all imagine a population of ticket sales. But a population of average ticket sales is something that's actually quite hard to wrap your mind around. And it turns out that we can say exactly what this normal distribution is. There's a result called the central limit theorem. And here's what the central limit theorem says. It says if we have a good sample, just like we found for the sample percentages, right? It's random. And now the sample size condition is going to be a little different. It's going to say, okay, we need either 30 data values or our variable has to have a symmetric mound shape. Now let's go back and think about this for our situation. Are these two conditions satisfied, right? So notice that we have a sample of what? Our sample size is 300. So we're definitely more than 30, and we need that because this is our variable, okay, not our sample means. This is our variable. Is our variable, does it have a symmetric mound shape? No. So because this is not symmetric mound shaped, okay, we need at least a sample size of 30, which we have. So we're okay. All right. So again, we have a random sample, and even though our data is not mound shaped, right? Our variable has a clear right skew, which we expect for financial data. Still, we have a sample size of at least 30, so we're okay. So what the central limit theorem tells us then is the following. It says we automatically get for free that the sample means have a normal distribution. They're centered around the population mean, and the standard deviation of the sample means is the standard deviation of my original variable divided by the square root of the sample size. And so let's go ahead and compare this with what we just did in our simulation. So we already verified that it's random and large enough. So we can automatically say that the sample means are going to be normally distributed. They're going to have a mean that's equal to the population mean. So what is the population mean? Well, let's go back and compute it. So I'm going to go back and compute the mean for the ticket price is my variable. And I'm going to find that that's 350.96, which is what we gave before. Okay. So 350.96. Okay. So the mean of the sample means is the same as the mean of the variable. That's really important. Okay. So the mean of the sample means is the same as mu, which we remember is the mean of the population variable. Okay, gonna move these over a little bit. Okay, and what was the so what's going to be the population standard deviation? Again, it's going to be the standard deviation of our population divided by the square root of the sample size. Okay, so let's go ahead and figure that out. Let's puzzle through that. So this is going to be equal to, and first I need the standard deviation of my variable, right? So I'm going to go into StatCrunch and pick that out, and that's going to be 101.55, my standard deviation of my variable, divided by the square root of the sample size, which is 766. So we'll put in square root of 766. And now we just go ahead and compute this, right? We can put this in our calculator or our phone or whatever, right? So we go ahead and compute that. And it's roughly 3.67. So 3.67. Okay. Notice it's not the same as the standard deviation of the variable, right? So this is what the central limit theorem predicts. Let's check this with what we got from our samples. So our sample was 350.8. That's not too bad. Oh, I'm sorry. I took samples of size 300, not 766. My bad. I apologize. This is 300. I'm thinking of the video we did earlier with the political campaign, right? Sorry. Our sample size here was actually 300. And it's usually a good idea to write these things out. Let me redo that calculation again, okay? And we get 5.86. Okay, so let's compare this with what we got from our previous calculations. So when we looked at the sample means and we took their sample, right? This is what we got. The mean was 350.81. Okay. Really close, right? 350.81, really close to what the theory predicts. And if we look at the sample standard deviation of our sample means, that's about 5.99. Again, very close to 5.86. So we can see that what we got from our simulations agrees with what we expect to see from theory. So that's good. Okay. Let's try a reading quiz problem. Let's actually try to work this out, okay? And do an actual problem. So here's what we want to do. We know that the systolic blood pressure for a healthy individual in your age group has a normal distribution with a mean of 112 and a standard deviation of 10. And suppose you go to the doctor and he takes your blood pressure. And we want to know, assuming that you're healthy, how likely is it your systolic blood pressure will be above 130? So this is a straightforward StatCrunch calculation like we did in the last chapter, right? You're given a normal distribution. If you go to normal calculator and plug in the mean and the standard deviation. Remember, when we're talking about how likely, that means percentile. And when our value is above the mean, we're interested in the upper percentile. So here I want the probability that X is going to be greater than 130. So you have to adjust that little option in StatCrunch. So go ahead and take a minute and compute that out. Okay. So let's go ahead and try our next question now. So the same sort of situation, okay, we're looking at blood pressures, same distribution, same mean, same standard deviation. But what happens a lot when people come into a doctor's office is they get nervous. Sometimes it's called white coat syndrome. And so sometimes what doctors will do is they'll take more than one reading and take the average. So suppose we take the average of 2 blood pressure readings. And I want to know whether or not that average blood pressure can be modeled using the central limit theorem. Can I use the central limit theorem? So what I'm doing here in this problem is I'm checking the assumptions, right? I want to check, is the sample random? And let's assume it is, okay? There's no reason to assume that the blood pressures are going to be different or that they're biased in any way. But notice the sample size becomes a consideration. My sample size is how many? 2. So I don't satisfy this. But is my data blood pressure, does it come from a symmetric mound-shaped distribution? That's what we want to figure out. Okay, so we're checking to see if the assumptions for the central limit theorem are satisfied, right? And so in part B, if they are, what is the mean of the sampling distribution? Okay. So in other words, if I'm thinking about what the distribution of the X bars look like when I have a sample size of 2, What is it? And we know from the central limit theorem what it is. The mean of the sample means should be equal to the mean of my population, right? And this is the hard question. This is the one that screws people up. What is the standard deviation of the sample means when n is equal to 2? And this is where it becomes really important to recognize that the population of the sample means and the population of the variables are different, right? This sigma is a standard deviation of my variable, blood pressure. This sigma sub x bar is a standard deviation of the sample means. So you're going to use this formula to compute this quantity. So go ahead and pause the video, and you can do that. Wait till the question comes up, of course. Okay, so now for the last problem. So same situation, right? I'm looking at systolic blood pressures, normal distribution. I know the mean, I know the standard deviation. Suppose you're a healthy individual and your doctor takes the average of your two systolic blood pressures. How likely is it that that average will be above 130? So what you're going to do is you're going to use what you obtained in the last problem. You're going to use the fact that the average blood pressures will have a normal distribution. And in this question, you figured out what the mean and what the standard deviation of that normal distribution is. And now you can use StatCrunch with the normal calculator to figure out how likely it is that your value is above 130. Okay, so the kind of recap, okay, we're looking at a quantitative variable. And this is a population where the population mean is mu, not the population in one category, sorry. The sins of cut and paste. And so we're repeatedly drawing samples of the same size that are random from this population. And what we're interested in is the population of estimators. In order to decide whether or not a sample mean could come from an old population, we have to know what sample means from that population look like. And this is the sampling distribution. The sampling distribution for the sample mean. Okay. And so our main result was the central limit theorem. It tells us what sample means from a given population look like. It says if we satisfy these conditions of randomness and either sample size or shape, either one of them, then the sample means we're guaranteed have a normal distribution. Their mean is the mean of the population of the variable, and their standard deviation is the standard deviation of the variable divided by the square root of n. Now, one of the things that's tricky about these problems is learning how to take apart word problems. So let me write one last slide that may help you a little bit, okay? So one of the things that we have to do is we have to learn how to read word problems. And you might remember I told you that statistics was not math, but we did have word problems. So the first thing you want to do when you're reading these word problems is you want to figure out what is your parameter. And the way that you're going to do that is you're going to look at the wording. You're going to look for the words either average or mean, which tells you you're working with a quantitative variable, right? Or percentage or proportion. And this tells you you're working with a categorical variable. And what you're going to do next is you're going to figure out what the variable is you're looking at. And the way that you can do that is it comes naturally from the problem, right? So it's always going to be like average of, okay? And that thing that's the average of, that's your variable, like the average height or the average weight or the average ticket price, right? That's my variable, ticket price. On the other hand, if I'm looking at percentages, right, it'll be, percentage of, and then it will tell me what the categorical variable is. So like in the first video, it was percentage of people who would vote for Trump. Usually a good idea to also identify your population. Who are you interested in? Okay, now you want to look at what comes from the sample. So you want to figure out what is your sample estimate and what is your sample size. So this is either going to be X bar or P, and this is your sample size N. And notice that if you're working with a categorical variable here, when you have population, in order to use the central limit theorem, right, you're going to have pi. If you're working with a quantitative, you need mu and sigma. So you're going to need mu and sigma. If you're working with a quantitative, or pi if you're working with a categorical. And it's always a good idea to kind of flesh this out. I myself do this, okay, because it's very easy to get turned around. So when you're working on a word problem and you have no freaking clue what you're doing, okay, sit down and do this. Just get your bearings first, okay? And what you're going to find out is as you go through and you go through this process, you're going to find that it's easier to kind of figure out what goes where. But the parameter is where you start. You're either going to see an average or a percentage. Okay, and that tells you what your parameter is. Then you figure out your variable from that. There'll be language. The average of what? Percentage of what? That's your variable. And you want to figure out your population because first, it's always a good thing to know what your population is. Okay, that's really basic. But you may have to get the mean and the standard deviation. And you're going to be careful because the sample is also going to have a mean. And this is why distinguishing between the population and the sample. Remember, we spent so much time talking about what's a parameter, what's a statistic. We're going to need that here because I have to use the population mean and the population standard deviation in the central limit theorem. So this is a good thing to get into the practice of doing, and especially when you're totally lost, when you have no clue what's going on, sketch out the problem, flow the problem, and this is how you do it. Okay, so good idea to start working the homeworks. If you run into any trouble, we're going to do some practice problems in the Zoom session. Okay, thank you.